Welcome back. We're on number 37 of our packet now. So let's get started with that one. On number 37, the owners of a water park want to build a scaled down version of a popular tubular water slide for the children's section of the park. The side view of the water slide, labeled ABC, is shown below. Points A prime, B prime, and C prime, shown above, are the corresponding parts of the scaled down size. Which of the following would be closest to the coordinates of a new point C prime that will make slide A prime, B prime, C prime similar to slide ABC? So if you look at these as both triangles, here the larger one with the water slide and here with the scaled down model, and they want them to be similar, that would mean that the sides would need to be in proportion. So that's the picture from the side. Over here is telling you how long. This one here says from A to C. You can't see it on my screen, but on your handout you can see it, that this A is at 1060. Let me write it over here for us. A is at 1060 on this chart here, this graph, and C is at 150.60. So the length of that segment from 10 to 150 is what you're figuring. So the length of this would be 140, and we're dealing with feet. So from A to C would be 140 feet. That's here, the base of the water slide. So that's 140 feet. Then we're trying to figure out how long from A to C would be in order for this, in order for us to figure out what this point over here would be. We know that the y is always going to be the 20 here because we're on, you can't really tell here, but we're on the 20 up. And then we just need to figure out what the length is of this base of A prime, B prime, C prime. Okay, so we also know that this length here is 20, A prime, B prime, you can see that here. And here, this height, I said length, but this height is 20, and then this height of the water slide is 60 feet. So we can figure out the ratio between the two slides, and I'll put the big slide over the little slide, 60 over 20. So our ratio is going to be a 3-to-1 ratio, the big slide to the smaller one. And we can set up a proportion to figure out what A prime, C prime is, because we know that AC is 140. You put AC over A prime, C prime. You can call that X if you want. You could call it A prime, C prime if you want, either one, just so you know what you're talking about. Then you want to cross multiply and solve this. So actually, if you make that an X, you can make it into an algebraic equation. 3x equals 140, and when you divide that 140 by 3, you get x is approximately equal to 46.7. And so the length of this A prime, C prime is going to be 46.7. We can just round that up to 47 because we're dealing in whole numbers down here in the answer. And this one starts at 3020. Our A prime is at 3020. And so our C prime, our 20 stays the same, would be at, adding 47 to our, it's actually 30, yeah, to our 30, that would give us 77. So our C prime would be at 7720. So you use the two models to figure out this problem, and remember, you want to pay attention to what you're reading. Similar means the sides will be in the same ratio, or the sides will be in proportion with each other, and you can cross multiply and solve. So hopefully that helped out with that one. 38, complete the proof by selecting the statement that best replaces the question mark. So here we're looking for a statement. Now in the past we have looked for so far anyway, we've looked for the reasons. This time we're looking for an actual statement. And here's what the reason for whatever the statement is Angle-angle similarity theorem. If two angles of one triangle are congruent to two angles of another triangle, the triangles are similar. So that's what we're trying to prove that we've got, or what the statement is going to be is by the angle-angle similarity theorem, two triangles that are similar. That's what we're trying to state. So if you just look at what you're given, you have AB is parallel to DE. So we look at that. You can also look up here at the given and see the same thing that we're looking at here. Okay. If this one says angle D is congruent to angle B, and angle A is congruent to angle E. If two parallel lines are cut by transversal, alternate interior angles are congruent. You've got your Z there and here. So by angle-angle similarity, the two triangles here and here are congruent. Now, though, that you have which angles are congruent to what, you can tell what corresponds with what. So the A will correspond with the E. So if I say, let's just say triangle ABC, because we'll just go in alphabetical order and we'll fix it down here. A would match up with the E. B will match up or be equal to the D, corresponds with, and C is congruent to itself. So we want to find the one that has that correspondence. A with E, B with D, and C with C. And looking down here, the only one I see like that will be the letter C. D matches up with B, E with A, and C with C. So answer C is your answer here. I was asked to try to pep this up just a little bit. It's kind of hard to do, but actually this one is not the one I need to pep it up with. This one might, oh, never mind. This one might be all right to pep it up. So let's see. Let's try a funny voice. How about, here we go. Here's the question. Is triangle ABC similar to triangle ADE? Justify your answer. Triangle ABC is the large triangle here, and triangle ADE is the smaller triangle here. You will notice that both triangles have an angle that is 120 degrees. Do you see? They also each have an angle here, angle A, that they share. Therefore, by the angle-angle similarity postulate, we have similar triangles. So yes, they are similar because angle A is congruent to angle A, and angle ADE is congruent to angle ABC, and they are both equal to 120 degrees. Thank you very much. Okay, so that's that. Hopefully that was a little exciting for you. Got a little laugh out of it. But this next one, we can't use a voice. We've got to be serious. We have a nice long proof here. And step number 8 might be a little bit confusing, but we will try to work our way through it. It says here, consider the proof below. Given that triangle ABC, given that you have triangle ABC, the larger triangle here, and that you know that DE is parallel to AC, we are to prove that the ratio DA to BD is equal to EC to BE. So we're proving that when you have triangles and you have a triangle and you have a segment that comes across that triangle and not necessarily at the midpoint, so it's not a mid-segment, but it's parallel to that third side, that it cuts these sides proportionally. So there's a theorem in there about that, but we're just trying to prove that theorem. So ABC is a triangle. DE and AC are parallel. That's given. Let's see what this says. If two parallel lines are cut by a transversal, corresponding angles are congruent. So what you're going to do is you're going to go up here to this picture and ask yourself which angles here are corresponding angles. So we have BDE corresponds with BAC. We also have angle BED that corresponds with angle BCA. Those are also congruent corresponding angles. But if you look on the next line, it says angle BCA is congruent to angle BED. BCA and BED, so it already covers these two. So we need to cover the other two. So here you would put angle BDE is congruent to angle BAC. Okay, because it already tells you here these are corresponding angles, and you just have to list the other pair. Nice. Then it says triangle ABC is similar to triangle DBE, because by angle similarity, they're similar, excuse me. Then all corresponding sides of similar triangles are in the same proportion. So if you take out those two triangles, BDE, and you look at it here, and you look at the larger triangle, BCA, so we're just looking at them separately here, then you can see the sides that are in proportion. BA, so left-hand side of the larger triangle, over BD, left-hand side of the smaller, equals BC, right-hand side of the larger, over BE, right-hand side of the smaller. Okay, then it has here that BA is equal to BD plus DA. So it calls it the partition postulate, but I would even say it could be segment addition, because if you add this little piece plus this little piece, you get the whole thing. And same thing over here, BC equals BE plus EC. Now what they do is a little substitution. From this, from step number 6 and step number 7, they combine the two, and they put this in for BA, so they substitute there, and they put this in for BC. Okay, so notice that's the substitution postulate. They're substituting that in for that. How do I know? Because down here, they separate it out, and they put BD over BD, DA over BD, and then BE over BE, and EC over BE. So what it would look like is this, BD in the step plus DA over BD equals, so we're taking from step 6 and plugging in step 7, BE plus EC over BE. So that's your substitution here. Okay, and you know that because if you look at the next step, you've got BD over BD, so you're separating this out, DA over BD, BE over BE, EC over BE. And so now what happens is BD over itself is just 1. Anything over itself is 1. BE over itself is just 1. And then if you subtract 1 from each side, you get DA over BD equals EC over BE. It's like magic. We're doing a couple of these that are kind of like magic today. And that gives you what they're asking for. Prove that DA over BD equals EC over BE. So voila, there it is. Equivalent quantities can be subtracted from each side of an equation. Pretty cool. Watch that over again, and also look on the Escambia website if you get confused by something, and you can always look back over it and see. I will be right back. Okay, number 41. Now, this problem is pretty complicated. In fact, I'm almost thinking I need to do a video just for this one. Or maybe just wait and do this one in class with you. It is pretty exciting, I think, but you might not. And I'm not sure how they would ask you a question about this in the EOC or on the EOC. So I'm thinking we're going to skip it for now and maybe come back to it at another time. This would be a good time for me to give you a code word or a password for 5th period. 5th period, your password is palm tree. And that will be the first person who brings that word to me on Monday. will get 5 points added to their formulas quiz on Wednesday. So palm tree, 5th period. 6th and 7th, you'll be coming up later. And 1st through 3rd, you'll be in a different video. All right, so for number 42, it says triangle ACB is congruent to triangle ECB. Oh, excuse me, ECD, shown below. So these two triangles are congruent. So we're switching back to congruent again. Now, you know what? Really, they're asking which statement is not true. You can just look at the correspondence here. You don't have to even confuse yourself by looking at the picture. You can turn it around like I did the triangles up top here on number 40. But watch, angle A is going to be equal to angle E. True. This says AC is equal to EC. AC, first two letters here, equal to EC, first two letters there. True. Then it says angle B is congruent to angle E. Not true. Angle B is congruent to angle D. So B is not equal to E. But remember, on the EOC, you can have multi-select. So you want to keep on going and make sure that you don't miss. AB is congruent to ED. So we are in luck. That's the only answer there. Sweet. All right. Cool. Number 43. In the figure below, segment BC is congruent to segment DA. Angle 1 is congruent to angle 2. CF is equal to AF. Complete the following two-column proof to show that triangle CFE, so this one here on the left, is congruent to triangle AFE. Let me mark those parts and pieces. We have segment BC, oh, tricky, is congruent to segment DA. Got it. Angle 1 is congruent to angle 2. Got it. Then it says CF is congruent to, I'm going to mark that. How can I mark that? This one here, I'll squiggly it, is congruent to AF. So the two squigglies are congruent to each other. And they are trying to prove that CFE, the one here, is congruent to AFE, the one here. Kind of looks like a hang glider when you put them together. All right, so here's their progression. They say that that's given, so that's the given information. Then they say why, they're asking you why is angle BEC congruent to angle DEA. This is one where I would say, hey guys, why can you say BEC is congruent to angle DEA? And hopefully to the screen you are saying, because Miss Gilliland, those are vertical angles, and vertical angles are always equal. Remember our vertical angle gang signs? Remember that. Too bad I can't show everyone else, if anyone else is watching, what vertical angle gang signs look like. Just imagine your V's. Oh, I can't even tell you how to do it. It looks silly. That's okay. Helps us remember vertical angles. And then it says what goes here for angle, angle, side. Well, remember, whenever you have angle, angle, side, 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 angle, side, angle, side, angle, if you have right, then you have hypotenuse, leg. That is always used to prove, those are your triangle congruence theorems and postulates. So we must be trying to prove two triangles congruent. Well, we have an angle here congruent to an angle here, an angle here congruent to another angle over here, and we have a side BC congruent to a side DA. So we have these two triangles are congruent. Very good. So that would be, and I have it listed here as the same way these two angles are listed. Triangle BEC is congruent to triangle, that's ugly, DEA by the angle, angle, side postulate or theorem. So after that, remember what I said when we were going through the other problems in class. Usually after you prove triangles congruent, the next step will be what? Can you remember? I'll give you a second. This says CE is congruent to EA, and those are corresponding parts of congruent triangles. What do we always know about corresponding parts of congruent triangles? That's right. I'm sure you said it. They're equal. So corresponding parts of congruent triangles are congruent. Remember that? CPCTC will usually be the reason for the statement that comes after proving triangles congruent. Alrighty, cool. Then CF is equal to AF because it's given, so they're bringing that back up. So the squiggly lines are congruent. These are congruent with a 3. Now, what can we say is congruent by the reflexive property that will help us prove the triangles are congruent? That thing right there is equal to itself. So EF or FE is congruent to EF by the reflexive property. If you got that, great. So now we have 3 sides of one triangle congruent to 3 sides of another triangle. Who remembers what that is? Side, side, side congruence. Very good. Hopefully you got that. 44. Triangles IJK and TUV are similar. The length of the sides of IJK are 40, 50, and 24. I'm going to put those in order from least to greatest. 24, 40, and 50. I'm just going to write them like this, and that's for IJK. It kind of looks like UK, doesn't it? The longest side of TUV is 275. It's asking us, what is the perimeter of TUV? Okay, so we need to find the other 2 sides. So here's what we do. We know that they are similar. Similar triangles' sides are in the same ratio. So if I put little triangle over big triangle and I reduce my fraction, I get 2/11. You are welcome to use your calculator for that. So I know that the ratio of my 2 triangles is 2 to 11. So if I say 2 to 11 equals 24 over x, that'll give me the shortest side of TUV. And if I say 2 over 11 equals 40 over x, that will give me the middle side of TUV, or the medium-sized side. Remember, when you have proportions, you cross multiply, and then you divide. So this will be the short side, 132. And over here we have 2x equals 440, dividing both sides by 2, x equals 220. So the medium-sized side will be 220. Remember what they're asking for. Always go back and reread what is the perimeter of the TUV of that triangle. So you want to add together 132, 220, 275. Remember, perimeter is when you want to build a fence. How much fence do you want? So you need to know the distance around. So you need to add up the 3 sides. So the perimeter is 627. And it doesn't give us a unit of measurement, so 627 units. That is number 44. All right, we're getting close. Let's go. DE, this one says, given that DE is parallel to BC, complete the following proof to show that the sides of triangle ABC are divided proportionally. Look at the proof we've got. And this proofs, as I've said before, are a great example of a drag and drop problem. On the EOC. DE is parallel to BC, given. You can construct, or excuse me, BA is a transversal that intersects 2 parallel lines. They're just pointing that out. Angle ADE is congruent to angle ABC. Why is that? Parallel lines cut by transversals always make you want to think of congruent angles. You want to think of these are corresponding angles. You want to think of the ones that make a Z, alternate interior angles. Those are congruent angles. Alternate exterior angles are congruent. You want to think of same side interior or supplementary. So there's so many things that you want to go back over and read from your notes and from your book from beginning of the year. But these are corresponding angles. Corresponding angles are congruent when lines are parallel. And then by the reflexive property, what would you say is congruent by the reflexive property? And remember, you are trying to show that the sides of triangle ABC are divided proportionally. So a reflexive property, what angle in here, because when you're proving triangles similar, you want to use the angle-angle postulate or side-angle-side, and we don't know anything about the sides, so we must need another angle. So using the reflexive property, angle A is congruent to itself. Now that gives us two angles. And now that we have two angles in this smaller triangle, if you're not sure, it's this smaller triangle ADE and this larger triangle ABC. So they have angle ABC congruent to angle ADE, and they both have angle A. So by the angle-angle similarity postulate, we have similar triangles. Postulate. Can't talk and write at the same time. Then we can just go one step further. You don't have to because you're finished, but since you have similar triangles, then you know that you have proportional sides. So that is pretty cool. And I'm not really sure about this reason here. To me, that doesn't make a whole lot of sense. But I don't really like that. But you've done your job if you stop right there. We won't overanalyze this thing. That's how you can say the two triangles are similar at least. 46, given the quadrilateral PART is an isosceles trapezoid, identify the missing statements in the proof to show diagonals PR and AT are congruent. So here really all you're doing is proving what two triangles would be congruent by side angle side. So we've got PR, you want to mark your triangle or your picture. This is a trapezoid. PR is parallel to PA. And they're also equal to each, no, excuse me, TP is congruent to RA. They're isosceles. And then angle TPA here is congruent to RAP down here. So, and then PA is equal to itself. So this down here is equal to itself. So what we have here are two overlapping triangles. If you want to look with me, we've got this one, PRA. I can do this to show you. That's not very good, but this would be PRA. We've got this marked, and this marked. And then if I look at the other one, you can kind of take them out and look at them. Sometimes that helps you to see better. And then you've got this marked and this marked. So now you can see that it's side angle side, and you can see the correspondence of the triangles instead of just trying to guess what matches up with what. You want to make sure your P matches up with your A, your R with your T, and your P with your A again. So B would be the answer here because P matches up with A both times and the R matches up with the T. And that's the only one where that happens. All right, we're getting close, y'all. Two more. Whew, this is a long one, isn't it? In the triangles below, angle P is congruent to angle S, and angle Q is congruent to angle T. The incomplete proof shows that triangle PQR is similar to triangle STU, which statement and reason are missing from step 4 of the proof. So we've got those are given. Congruent angles have equal measures, so their measures are equal. The sum of the measures of the angles of a triangle is 180. Then after that, we have the measure of angle R is equal to the measure of angle U. If equals are subtracted from equals, then the results are equal. So apparently what we're trying to do here then is to find a step that goes between them, all three of these angles from the one triangle adding up to 180, all three of these angles from the other triangle adding up to equal 180. And then what we need to do is be able to subtract P and Q from this one and S and T from this one to leave us with R and U. And you can do that because If two quantities are equal to a third quantity, then the two quantities are also equal to each other. So you can write this way, since they're both equal to 180, you can set them equal to each other. So these three added together equals these three added together. And then what they do to get rid of the other two is what I was talking about. Since P is equal to S, you can subtract those. And since Q is equal to T, you can subtract those, and you'll be left with the measure of angle R is congruent to the measure of angle U. Ooh, fun. Last one, Malik runs on the trails in the park. He normally runs one complete lap around trail ABCD. The length of each side of the trail ABCD is shown in meters in the diagram. If trail EFGH, here's that word again, is similar in shape to trail ABCD, what is the minimum distance to the nearest whole meter Malik would have to run to complete one lap around EFGH? So what we have to do here is figure out the ratio of what we do have. And what I did was I turned my small trapezoid around so that they would match up. Because right now the sides do not match up for corresponding parts. Now this isn't going to be perfect or pretty, but the B matches up with the F. I should have started with A. The A matches up with the E, the B with the F, and the C with the D. So I turned mine around so I could get a better perspective of what matches with what. And from up here, the BC is 47, CD is 90, the AD is 100, and the AB is 45. Now, because they're similar triangles, I can come up with a ratio because CD matches up with GH. So I can do my ratio and say it is 9 over 100, which will be 9/10, and that's going to be my ratio for each of the sides of my trapezoids. So I can do that for every side. So I set up 9/10 equals 47 over X, 9/10 equals 45 over X, 9/10 equals 100 over X, and I already know the other side is 90 and 100. And I cross multiply, and I get, for this one, this is my ratio that I'm working with, ratio, okay. Hey, 6th period, your code word is going to be ratio. 6th period, your code word is ratio. And then from there, I cross multiply. 9x equals 470, and that's going to give me 32.2. Then this one, 9x equals 450. That's going to give me 50. This one will give me 9x equals 1,000, which is 111.1. All these are estimates. Well, not all of them, but those are estimates. So I'm going to put that over here. And actually, that's not 32.2. Excuse me, that's 52.2. My fault. So I'm going to put FG would be 52.2. We know that GH is 100. EH is 111.1. And EF is 50. And I'll add those together, and the perimeter would be 313.3 meters around that largest track to complete one lap around. And it says to the nearest whole meter. So I will put 313 in my boxes. 7th period, your code word is Gus, because Gus is sitting beside me as I do these problems, as I work these problems. I hope that that was helpful and useful for you, and I will see you on number 49.